All right, this is part 2 of our notes on polynomials. So we're going to talk here, this is the top of the second page of our notes, on the rational root theorem. The rational root theorem, it provides a list, so it lists all possible rational roots of a polynomial. Notice that we say rational roots. These are roots that can be written as a fraction. So for example, you could have a whole number, you could have a fraction, but we wouldn't see any square roots or anything like that. The way we find that list of possible rational roots is that we take all the factors of the constant term. So the factors of the constant term, the number with no variable, divided by all the factors of the leading coefficient. And the way we list those is we call all the factors of the constant a p-value divided by all the factors of q, the leading coefficient. So what do we mean by this? Well, if I wanted to find all the possible rational factors of, say, this polynomial here, I am going to take all the factors of the constant term, which is 2, and all the factors of the leading coefficient, 15. And if I want to figure out all the possible rational roots, it would be plus or minus 1 or plus or minus 2, and all the combinations we could create with the factors of 15. I think I skipped over plus or minus 1 here. So all the possible zeros written out in a list here is it could be plus or minus 1, it could be plus or minus 2. It could be 1 divided by 3. It could be plus or minus 2 divided by 3. It could be 1 divided by 5. It could be plus or minus 2 over 5. It could be plus or minus 1/15, and it could be plus or minus 2/15. These are all the possible factors of this polynomial that we could see on a graph. Now from here, we can graph to find our solution set, and that set of numbers with a graph would be -1, -1/3, and 2/5. We can see all three of those are written as rational solutions, and we can see each of them show up in our list, right? There we get -1/3, and there we have 2/5. As you can see, we'll come back to this idea of finding zeros as we go. More vocab to find the y-intercept, just as we would on any other function. We are going to let x equal 0 and simplify. There's always only one y-intercept, whether it's a polynomial or any type of function. If there were more, we wouldn't have a function. We'll also deal with this idea of turning points. These are the number of times our graph switches from increasing to decreasing. The number of turning points will be at most one less than the degree. It may not be just one less than. That represents the most possible turning points. So for a third degree polynomial, we would have at most 2, but we could have 0. We can also call these turning points relative max and mins. And colloquially, we can call them These are just our peaks or our valleys, right? These are points where our graph hits a high point and then falls, or hits a low point and then rises afterwards. So I'm going to talk through this. I know that these graphs can sometimes be frustrating, but I want to talk through the key things we can find algebraically and what we can kind of plug in along the way to make things quicker. Well, here I have a polynomial. It is 4x to the fifth plus 12x to the fourth minus x minus 3. And I'm going to try to factor this. I'm trying to factor this so that I can find my x-intercepts. I can see that I have 4 terms, so I'm going to factor x to the fourth out of my first two. You know what, let's make that 4x to the fourth, and what will remain will be x plus 3. I'm going to factor a -1, and I'll have x plus 3 again. Again, these are all set equal to 0. Once I factor out that x plus 3, I would be multiplying times 4x to the fourth minus 1. Now that is a difference of perfect squares, so we can write this in fully factored form as x plus 3 times 2x squared minus 1 times 2x squared plus 1, all equals 0. That means we will have x-intercepts at plus or minus 1/2, and we're taking the square root there, as well as -3. Just so we know, we can rationalize this. This would look like root 2 over 2. So those are our x-intercepts. We can plot those. And then we also want to find our y-intercept. This one's a little bit easier. All I need to do is plug in 0 for x. I can see that my first, second, and third terms would fall away, and I'd have a y-intercept at -3. So I'm going to go ahead and just pause here for a minute and set up my graph. I'm going to plot my x-intercepts and my y-intercepts, and we'll talk a little bit about end behavior. All right, folks, you want to take a quick look at what I've done so far with my graph. I've plotted some key points. I decided to scale my graph up a little bit in the horizontal direction. So every box you see is worth half of a unit. So you can see here that I've plotted my 3 x-intercepts, one at -3, one at negative root 2 over 2, and one at positive root 2 over 2. You can see I'm using approximately 0.7 for that expression. Now, I need to figure out what else is going on with this graph, so I need to use my leading coefficient test. I can see that I have a positive lead coefficient and that I have an odd degree. What that tells me is that as my graph goes to the right, the positive lead coefficient will tell me that my graph will go upwards. And I know that odd degree polynomials always have graphs where they end opposite from where they go in the positive direction. Now we'll get into more details about what fills in the next parts, but really we just need to construct a graph that hits the key points of our intercepts here. And so what we've really done is we've highlighted key points we could find algebraically, our x and y intercepts, and then also based on the leading coefficient test, we've identified that we have an odd degree polynomial with a positive leading coefficient. So it gives us a pretty quick way to sketch a pretty complicated graph. We will finish up this part of our notes here with the intermediate value theorem. This is one of those very intuitive things that we can do in math that we don't have to fight our brains too much on, right? So here's what they tell us. This is somewhat confusing the first time through, but if f of a and f of b have opposite signs, then on the interval from a to b, including the endpoints, there is at least one value for c that equals 0. In other words, if I am on a graph and the output of the graph switches signs from positive to negative or negative to positive, there must be a point where it is neither positive or negative, or that it is on the x-axis. In other words, C is a root. So let's just make sense of this. If we say that f of negative 2, and we can find this through synthetic substitution, 1, 1, 0, 1. And I'm just using my synthetic division process to use synthetic division here. So f of negative 2 is negative 3. It matches the remainder. And I'm going to do the same thing with negative 1. I'm going to use those same coefficients and synthetically substitute. So 1, negative 1, 0, 0, 0, 0, and 1. So f of negative 1 is 1. What we're saying here is that between negative 2 and negative 1, we will find an x-intercept. We can see that f of negative 2 is negative. It's negative 3. And f of negative 1 is positive. It's positive 1. Because we go from negative to positive, and because all polynomials are continuous in that they don't have any gaps or jumps or asymptotes or anything like that, there must be an interval on the there must be a root on the interval negative 2 to negative 1. We could use our graph to find, I think in this case, it ends up at a decimal, negative 0.755, and I just got that from my graphing calculator. But this intermediate value theorem tells us that if we go from positive to negative, there between, say, 5 and 10, there must be at least one x-intercept on that interval from 5 to 10. So we'll call that, we'll call it there for part 2. I think we should be able to finish up the remaining notes in part 3. Thanks, guys.